Yes, so I'm making it live.
Okay. Okay, you are. I think I can see that. Did anyone join? I think no one, right? Okay, fine. Let me wait for some people.
Yes, Naveen, let's start now.
Okay, no one is there. Can I start?
You can.
Okay, fine. Start recording here. Okay. Good evening, all. So let's start the session for today. So today I'm going to start the uh, discussion on manufacturing and industrial engineering. So this is one of the key topic in mechanical engineering, right? So this is a demo session for mechanical engineering, and this will come in section 4. If you go to the GATE syllabus, you can see in the section 4. So now let us see. Okay, fine. Let me introduce myself. So my name is Naveen Kumar. I did my bachelor's from IIT Kharagpur, master's from IIT Hyderabad, and then I have joined at PSU for 1.5 years. I worked as an executive trainee there, and then I went on to pursue my PhD in IIS Bangalore. I'm in the final stage of my PhD. So coming to my GATE experience, I have 7 years of teaching experience in especially GATE across different states in India. Okay. So let us go and give. Let me give you some small introduction on what is manufacturing. Okay. So okay, before that, let's go for the syllabus. Okay. So the syllabus is this much. You can see here in section 4, we have engineering materials, we have casting, forming, and joining process, we have machining and machine tools operations, we have metrology and inspection, we have computer integrated manufacturing. All these things will come under materials and manufacturing. And if you see the industrial engineering syllabus, that is in the next slide. So this is the industrial engineering syllabus, that is production planning and control, inventory control, and operations research. So this section 4, both materials manufacturing and industrial engineering, is, I can approximately say that it is 1/4, a quarter of the whole GATE syllabus Coming to the marks also, you can expect approximately 25 marks out of 100 in this syllabus. So that's how it's very important, and it's not a subject which you can leave. It's very, very important, right? So let's for today I'm going to discuss the topic of machining and machine tool operations. In that, we're going to give some introduction on that. But before going to this topic, let me give the syllabus. Of course, weightage. So the weightage you can see here, right? 17 approximately plus 7, right? Will give you approximately 22 marks. So approximate is around 22 to 24 marks, right? So that is what is manufacturing engineering and industrial engineering. Right? So these are the reference books. If you want, you can follow them. So this is one of the good book that is by Amitabh Ghosh and Ashok Kumar Malik. And rest of the books, most of you know. If you do not know, no problem. You can download these books from online, and then you can refer them. And if you have any doubt, I feel the notes what I'm giving or the slides that I'm providing are good enough for you. Without any reference from these books, you can go ahead with the gate questions. But still, if you want to refer, you can go through these books. And for industrial engineering, these are the books. And now let's go into the topic, that is manufacturing, right? So what is manufacturing? The manufacturing is, in a broadest sense, is the process of converting raw materials into valued products. Okay. So what is converting raw material into valued product? So let's say that we have some raw material. So where do you get raw material from? We get raw material from earth, right? So this earth, so this is earth, and from here we get the raw materials, right? So raw materials, right? So from here you do the mining, right? You dig out and get the crude raw materials, right? And from this crude raw materials, you do some metallurgical operations. So I can write here, let me write something like, mining, right? This is metallurgical, right? And then after refining them, you get some raw material. I can say some kind of material which is processed. So I can say processed raw material. Right? Processed raw material. Now from there, I can do some manufacturing process, or I can say some kind of method where we can convert this raw material into valued products. So this is what is your manufacturing. There are stages in manufacturing. Let's not worry about that now. Okay. And now you get a valued product. Or you can say a final product. Right? And are we going to use them? Are we going to use finally? Of course, we are not going to. We are going to use, but before using, you got to do one step. That step is, I guess you have in your mind, that is inspection. You inspect it. Right? Once the inspection is done, then what do? You get a good one and a bad one. In the sense, I can say a bad or poor product. I can say a poor product in the sense like there is some kind of a defectiveness in that. So let's write that as defective product. Right? And this is good product. If you have good product, there's no problem. There's no problem at all, right? if you have defective problem, it means that there is some error in either metallurgy or materials or manufacturing or design. Anything can be a problem, right? So this is what is your feedback. Some defective products, you can get the feedback, and that feedback, right, you can pass it to the manufacturing, you can pass it to the raw materials, you can pass it to design also, right? So this is what is your error. Right? So this is some kind of a closed loop system. It will keep on improving as and when required. Okay. So the same thing we can see in this diagram as well here, right? So what can you see here? What can you see here? First, there is power. Say first there is a blank. So this one is called raw material. Right? And this is number one. Number two, you need to have a machine, of course. Right? Number three, if you have a work material, you have to fix somewhere. You have to fix that work material somewhere to do some operations on that. It can't float on the air. It should be placed somewhere in certain positions with some clampings. That's it. That's what is called fixture. So you have a fixture. In a machine, you have a fixture. In that fixture, you're placing the raw material, and then you have certain tools, right? And you have to provide power to the machine. It's very important, right? And then you have some specific environment provided to the operation, right? So here it is machining, but you can replace it by manufacturing also. Anything is fine, right? So specific environment. What is a specific environment? I can think of some specific environment, like you have to provide some coolant in machining operations. Coolant can be one of the operation, when one of the environment, right? That is 6, let's say. And another thing, very important thing that we're missing here is manpower. Right? So we have manpower. Then once all these inputs are given to the machining process here, you'll get a valued product. This is your valued product, which is having some value at the end. Right? Valued product. And once this valued product, you got the valued product, you come down, you do the analysis. And this analysis is nothing but inspection. See, that analysis will do some error, right? That error is some kind of, this, you can say this is some kind of error, right? And that error can go into the correction, and that correction will be sent into the environment, tool, fixture, machine, blank, etc., etc., etc. Okay, so this is the complete understanding of manufacturing, where we can convert raw material into the valued product. Okay, now, so if you see here, we have some product here, and I guess you can see from here itself, that is your bolt. So what is the input? Input is some kind of a raw material. You can say it is some kind of a cylindrical billet, right? And that will be going in some stages of processes, and then that is what is your process here. You can see here on the top of it, you can see the process here. This is the process. What happened? So this is the process. This is the process. This is the input, and then you get the bolt as output, right? So you have some input process, and then you're getting some output product. That is what is your value added. Okay, so this is the complete understanding of manufacturing. Fine, let's proceed. Now let's go into a subsection of manufacturing, or subsection of machining, I can say, that is metal cutting. Right now, so what is metal cutting? So before metal cutting, we'll discuss about material removal process. Okay, so the material removal process is nothing but we have some manufacturing process, any manufacturing process. You can think of drilling, boring, grinding, lathe machining, anything you can think of. In that, we are going to remove the material. In this figure, we can clearly see that there is some kind of material removal that is happening, right? In this figure, we can clearly see that there is some kind of material removal that is happening. So this is what is your chip, this is your workpiece, this is your tool. We'll label them. But let's read the statement here. Material removal process is a manufacturing process in which excess material is removed from workpiece in order to shape into a desired final product. So have some kind of, in the previous thing also we have seen. If you see here we have some kind of a cylindrical. So I can say that there is some kind of a cylindrical billet here, right? This cylindrical billet has converted into this kind of thing, right? The same way, I have some kind of material, raw material, and I remove material slowly in the form of chips. If you are thinking of machining, lathe machining, grinding, milling, drilling, you're removing the material in the form of chips, right? But in some other machining process, you can remove in the form of some kind of melting and evaporation. So based on the manufacturing or machining process, we'll be able to tell you how the material removal rate is happening, right? So material removal process is some kind of removing the material from the workpiece to get the final desired product. Now, so there are so many processes. Why so many processes? Because for certain process, you get some certain required finish, surface finish, how smooth it is, right? And if you have some very hard material or very soft material, you have to go for some specific machining or material removal process. Or based on accuracy, you have to go for different material removal process, right? So the choice will depend upon work material here, work material, desired accuracy, and required surface finish, right? Next, the goal of this process is to get good dimensional accuracy, surface finish, of course, with minimal waste of material. So you don't want to remove so much of material, right? You have to have your raw material, and then upon that, with minimal amount of material removal, you should be able to get your final desired product. Good. So if you see here, there is some kind of uh, we can label them. If you want, we can label them, right? So what is this? I can say this is, the color is not matching. Let's take black itself, or maybe we'll take blue. So this is the thickness also is different. Fine. So this is chip, right? What is this? This is tool, and this is your workpiece. Workpiece, sometimes people even often call as work, right? So you are having some kind of tool on workpiece. You are removing the material in the form of chips. And please remember, in conventional material removal process, tool should be harder than workpiece. It means your tool should be means your workpiece should be softer than tool. Harder tool should cut the softer workpiece in the form of chips. Good. Now let's proceed. So let's classify this material removal process. First one, there are four classifications. Classification number one, with the classification with respect to cutting process, with respect to abrasive process, non-traditional process, and hybrid process, right? So what is cutting process? That involves cutting or removal of material from the workpiece. In cutting, in this, we will ask, sir, everything is material removal process. Why you are saying cutting? Cutting in the sense in the form of chips, bigger chips. Okay, so I can use I can say turning is one of the example, milling is another example, and drilling is the another example. So this will come under one classification, right? And then another classification is abrasive process. It means that abrasives, if you see what are abrasives, abrasives are nothing but small, right? It can't be, we cannot say how small, relative small materials, which are harder materials mixed in some kind of, other secondary fluid, or maybe mixed in anything can be happening. So that, or else this harder materials can be, bound together to some kind of a wheel, then it will come into a grinding wheel, right? So these abrasive particles will remove the material, and that kind of processes are under abrasive processes. For example, we can say grinding, right? In grinding, you might have seen there's a grinding wheel. In that, we have some abrasives. As the grinding wheel rotates, the material will be removing. So all this process, I'm just classifying here itself. If you're not understanding, if you're not knowing anything about grinding or turning or milling, don't worry. The coming classes will clearly take one of the topic, each topic separately, turning, milling, drilling, and all these things. Clearly, we'll discuss what is the process, what is the method, what is the tool that we're going to use, and what is the mechanics, force analysis, power analysis. We are going to do everything, right? Next, honing. Honing is one of. So if you remember what is honing, you might have seen in your villages, especially it will be available in villages, like where they pour all the some kind of seeds or some kind of dal and all inside, and they'll have some kind of rolls. They'll put all these materials, and you just put it here, and then you rotate the up one. So through that rotations, that will get abrasion, right? And because of that abrasion, the abrasive particles will remove the material. So if you do not understand this also, no problem. We're going to discuss that in the coming slides. And next, another example for abrasive process is lapping. Okay, good. Now, so another classification is non-traditional. So in the previous ones, we have seen the classification of traditional machining. So I clearly said that in traditional machining or conventional machining, workpiece material should be softer than tool, or I can say tool should be harder than the workpiece material, right? And in the non-traditional process, there is no need for the tool material to be harder than the workpiece. And also in the previous process, we can see that there is a physical contact between workpiece and the tool. I mean, tool has to touch or contact the workpiece for the material to get removed. But here, it's not required. In non-traditional process, it may or may not required. Generally, it is not required. So you might say, how without contact? Yes, through different energy sources, I'm going to use. So if there is a contact, you are using mechanical force. If there is no contact, I'll be using some other different forces, electrical energy, right? Chemical energy, right? Light energy. There are so many energies I can use. So such kind of processes are known as non-traditional machining processes. Right? Example, electrochemical machining, electro-discharge machining. So electrochemical machining, there is a shortcut for it. It's called ECM. Right? We'll discuss that. And then this is EDM, that is electric discharge machining. Right? So electrochemical, electricity and chemical energy. Electro-discharge, right? Electricity, and there is some kind of potential difference. Because of the potential difference, there is some kind of sudden discharge of electrons. There is a big process that is happening for electro-discharge machining. We'll discuss that. And laser, this is light, right? Light, some high density, high powered light is laser, right? So you can use that also for heating and then melting and evaporating. You can remove the material there also. Next is hybrid process that combines the principles of cutting and abrasives. In the previous one we have seen, right, cutting and abrasives. So it can combine both, and you can say electrochemical, abrasive jet machining, ultrasonic machining. These are also some kind of non-traditional processes only. Hybrid processes are also known as non-traditional machining process only. So there's so many processes. So there are a wide variety of processes. So each one has a specific advantage and a disadvantage. So we'll be able to try to pick one of it which is having so many advantages for a specific material that you are going to machine. Right. Next. So let's go in detail into metal cutting. Right. What is metal cutting? Metal cutting is again removal of material from the workpiece or excessive material from the workpiece. See, I highlighted them. Excessive material, removing excessive material from a workpiece in the form of chips to shape it into a desired final product. So chips are very important. If we are cutting a metal or by removing the excess material from the workpiece by tool should be harder than the workpiece in the form of chips. Good. Next. The cutting tool is typically of high speed steel, HSS you can see, or a carbide. Why carbide? Carbides are generally having high strength and hardness. Carbides. So you can say a material which is having good amount of carbon in it. Generally, they are very strong in nature. Let's say if you take, diamond, right? Some tungsten carbides. So carbides, every time you mix carbides into it, all these things are having good amount of carbon in it, which gives high strength and hardness to the work material, and that material we can use as tool to remove the workpiece material in the form of chips, right? And is designed to withstand the high cutting forces and temperatures involved in the process, right? So this, why this carbides and high steels we are using? We are using to maintain the temperature, because if at all high temp, because there is a contact between the tool. So you can see if you want to let's nomenclature this. Let's label them. So what is this? So this is a tool. You can see. Let me use sticker only. So this is the tool, cutting tool, right? And workpiece material, right? This is original unmachined one, and this is machined surface after machining, right? And how does this remove? You can rotate the workpiece with the help of headstock. You have some kind of headstock. This is put in a lathe machine, right? This is headstock, and you can support your workpiece through a tailstock here, right? This is headstock. This is tailstock. Right? And you can remove with the help of chip. So whatever is coming out here is chip. You're removing with the help of chip. Right? So what is this N? N is nothing but RPM here. Please do not forget, this is N, the rotations that are happening in the workpiece. Right? So tool should be harder and workpiece should be soft. That is important. Remove the material in the form of chips is known as metal cutting. Good. Now, so again, I'm emphasizing the important point, that is materials are removed with harder tools. So if you see, all these things are some kind of machining process. So I hope if you want, you can pause the video and just name each of it. So let me name all of them slowly one by one. So this process is lathe, right? Lathe. And this is what? Anyone? Yes, you can say this is milling, but there's a specific name for it, face milling. Especially, okay, let's not go for lathe. The operation will go. So the operation is turning. Good. This is face milling. This is end milling. I hope this is very clear. This is drilling. And of course, this is grinding. Okay. Each one is different with respect to cutting tool, with respect to the rotation of cutter, with respect to the movement of workpiece. Everything is varying. So we'll discuss each one of it very clearly in the coming slides. Good. Next. So in all things what I've shown in the previous slide are cutting tools. So this is one cutting tool here. You can see here. This is one cutting tool. 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 So here it is called a single point cutting tool, lathe turning tool. This is a face milling tool. This is a end milling cutting tool, or face milling cutter, end milling cutter. Drill bit, you can say. Grinding wheel, I can say. Right. So some of them are having single point. Some of them are having multi-point. Right. All these things are important for us. Why single point? Why multi-point? Who is better? What? All these things we have to see. Right. Good. Now, so speaking of cutting tool, what is cutting tool? Cutting tool is nothing but is a tool used to remove the material from workpiece. Please understand there is a difference between cutting tool and machine tool. Machine tool is different. Cutting tool is different. So I have just given a note below. A machine tool is a machine. Cutting tool is a tool only, but machine tool is a machine itself. It's very important. Okay. So cutting tool is a tool used to remove material from the workpiece. And a machine tool is a machine designed to shape or form the workpiece, or it can provide holding of this tool, and that tool is given some relative motion with respect to workpiece, and then cutting process is done in the machine tool. All this cutting processes is held in a machine tool with the help of a cutting tool. Okay, so the example for machine tools are lathe machines, milling machines, drilling machines, and grinding machines. Right. So what are the different cutting tools we have? This is a lathe cutting tool. Drill bit, I can say this is a single point lathe cutting tool. Drill bit, this is your face milling cutter, and this is your grinding wheel. Right. So let me write them, each one of it. So I can say lathe cutting tool. This is drill bit. Milling cutter, face milling cutter. This is grinding wheel. Good. Right. So you can easily see this one is a single point cutting tool. This is a multi-point. But if you go in deeper and see, drill bit are having only 2 cutting points. People think drill bit is having 1 cutting point. No, drill bit will have 2 cutting points. We'll be discussing that. Okay. So with this, we can say there are single point cutting tools and there are multi-point cutting tools. Right. So let's discuss them. So single point cutting tool. So what is single point cutting tool? Single point cutting tool is having a single cutting edge in contact with workpiece. Only one cutting edge is in contact with the workpiece. So if you see here in this, so this is one cutting edge and this is another cutting edge. Right? That highlighted parts are cutting edges. Any one of it should be having contact. So generally, this is the So I can say this is the 1 and 2. First one is the main principal cutting edge, and that is what is it will be in contact with the workpiece. So will be discussing this in detail when we're discussing separately about single point cutting tool. But speaking of single point cutting tool, I can say that one, especially this cutting edge will be in contact with the workpiece, and that's why this single point cutting tool or lathe where we are using this tool for turning, so this will be called as single point cutting tool. When it is multi-point cutting tool, when more than one cutting edges are in contact with the workpiece material. That's it, right? So what are the different things cutting edges here? I can say the different cutting edges are. Okay, let me use red only. Right. So this is one cutting edge. This is another cutting edge. Right. This is one cutting edge. This is another cutting edge. So there are so many cutting edges here, right? And all these cutting edges, or you can say if you're in 2D it's edge line, in 1D it is point, right? So cutting point, these are all cutting points. These dotted ones are all cutted points, multi-point cutting tool, right? So this is what is your end milling. Sorry, this is what is your slab milling. I can say not end milling, slab milling, right? So this is what is your cutter, right? And this is your workpiece material, and the feed is given to the workpiece here. Oh, a new term, feed. Okay, we'll discuss that. Feed. And here the rotation is given to the cutter, right? And the distance between unmachined surface and machined surface is depth of cut. We'll discuss that in the cutting parameters, right? Cutting characteristics or cutting parameters. We'll discuss that. On the right hand side, again, we can see it's a drilling, right? And we have two cutting edges or two cutting points. Those are this and this, right? 1 and 2. So this is what is your drill bit. And you have two cutting edges, two cutting points. Okay, so this is your workpiece. Good. Now let's proceed. Different cutting tools examples can be given. For single point, for single point, you can name some examples, right? Those are already we have seen the turning tool, right? So I can say turning tool, single point cutting tool, right? And I can say maybe shaping tool, right? Shaping tool is one of the another cutting tool where we have only single point cutting edge, cutting point, right? Parting tool, I can say parting tool also is an example for that, right? And in the case of multi-point also, we have some examples like, milling, drilling, all these examples. So I can say grinding wheel also is another example for multi-point, right? Hacksaw blade also is another having, multi-point. All these things will come under multi-point cutting tools. Okay. Let's discuss now what are the cutting process parameters. Okay. So I told you a term called feed. So we're going to discuss, there are three important cutting process parameters: speed, feed, and depth of cut. We're going to discuss them in detail now. Speed, feed, and depth of cut. What is speed, what is depth of cut, and what is feed? Okay. Now, let's first write what is speed. Speed, right? Speed is generally, in the case of machining, is represented by number of rotations made by workpiece or cutting tool. But here, as we are showing the example of lathe machining, that is turning operation, I can say the rotation is given to the workpiece. Hence, I can give the rotations to the workpiece. Okay. So the rotations are given to the workpiece like this. Number of rotations. Okay. So I can say it can be represented by n, and this n are RPM, rotations per minute. Right? Okay, this is your axis. If you see, this is your axis. This is your axis of rotation. Okay. Now, the number of rotations are happening per minute is given by n, and it can be converted into velocity. How velocity? Because I can think that this thing is coming out as a chip, right? This is coming out as a chip. Let me write that. It is coming out as a, okay, color is not matching. Let me take some other color. Chip. This is what is chip. Good. Very good. Right? So the chip is coming out as this is rotating. So there is some kind of velocity that is happening. There is some kind of relative velocity that is happening between the tool and workpiece. So this is tool here, right? This is tool, and this is workpiece. Right? Relative motion is what is your velocity. The chip is going out, and there is a relative motion that is happening between tool and the workpiece. And that is what is your cutting velocity, sometimes also known as cutting speed. Number of rotations are given as RPM. So sometimes cutting velocity is given, we have to convert it to RPM. Sometimes RPM is given, we have to convert it to the cutting speed. Right? So how can we convert that? We can convert them by using this formula. We already know that. You have some circular motion, you want to convert it into linear speed. How do you convert that? Cutting velocity V is equal to pi dn by 60. You can write pi dn by 60, you can write pi dn by 1000, you can write pi dn also. But when we have to write what? It will depend upon the units that you are considering. So let's assume that the diameter of the rotation, the workpiece is rotating with some diameter d. So let me take the diameter here. So let me take a line. Sorry. Okay. This is your diameter d. Diameter of the workpiece. Let me write that. D is diameter of workpiece. Okay. And now I can say the cutting speed is pi, n is RPM, V is cutting velocity. By 60 is given only when the units are millimeter per second. N should be in RPM only, rotations per minute. Diameter should be in mm. Okay. And now here it can be pi dn also. When it can be pi dn? When diameter is in mm and you're not dividing it by 60. As you're not dividing it by 60, it will come as meter per mm per minute. Let's assume that diameter is in meters. Then, if diameter is in meters, it will be pi dn by 1000. This is meter per minute. So, in these two cases, diameter in mm, in this case, diameter in meter. Good. Okay. Next one is feed. So, what is feed? And it is represented by small f. So, if you see here, the tool is going in this direction. Tool is going in this direction, right? The tool is going in this direction. And as it is going, you can see there is some kind of movement that tool is happening for each rotation. For one rotation of workpiece, the tool is moving in this direction. And that is what is your feed F. And I can say, okay, let me take this thing. I can say that this distance that is happening in one rotation is your F. The small distance that you can see is known as feed small f. So I'm saying relative. For one rotation, how much the tool is moving in this direction. Again, I repeat. For one rotation of workpiece, what is the distance of this tool moving in this direction is the feed. So in exactly one rotation, this is the F. In another rotation, it will move the same amount of F. In another rotation, it will move the same amount of F. So it will keep on proceeding like this. So that is what is your feed. And the feed will be given in this direction. And another thing is your depth of cut. So before giving, saying the speed, going to the depth of cut, I would like to write the units. I'll write the units. What are the units of feed? It is mm. Movement is happening in mm. Tool is moving in this direction in mm. And rotation is happening. So I can say it is mm of tool movement for one rotation or per revolution of the piece. That is what is your feed. Okay, next is depth of cut. Okay, so let me write that. Depth of cut. And it is denoted by small d. Okay, so what is depth of cut? Let's come to the figure here. The tool is sent inside. It is given some movement inside. Okay, what is that? So let's write what is that. So the tool is given movement in this direction. Okay, right, and that is visible here. And that is what is depth of cut. So you can see this one, this distance you can see is your depth of cut because of the tool plunging into the workpiece can be visible here. That is what is your depth of cut inside. You're going inside. So that is what is your depth of cut D. So you are giving D inside, depth of cut direction D inside. So you can vary the depth of cut as the tool, the machining is happening, or you can keep the depth of cut constant also. If you're putting the depth of cut constant, the diameter after the machining will be constant throughout. throughout the length, or if you're varying it, you'll get a tapered diameter, right? So depth of cut is given as what? So this is what is your unmachined surface, if you see. So this is what is your unmachined surface, and this is what is your machined surface. So this is unmachined surface, this is the machined surface. So the depth of cut definition can be like this. It is the perpendicular distance. This is what is the perpendicular distance, right? Distance between the unmachined surface to the machined surface, right? Sometimes unmachined surface is also known as atmospheric surface. Okay, so let me write that here. So to make you understand, so this is what is, okay, let me take another ink here. Okay, this is atmospheric surface. And this is machine surface. So the perpendicular distance between the atmospheric or unmachined surface and the machine surface is known as depth of cut. Okay, so let me write that. Depth of cut. Perpendicular distance between machined surface and atmospheric surface. Machined surface and atmospheric surface. Good. So now we are done with all the three cutting process parameters. Those are speed, which is in RPM, feed, which is F in rotations of, for one rotation, what is the movement of tool? So 1 mm of tool movement per one revolution of the workpiece. Depth of cut is the perpendicular distance between the unmachined part and the machine surface. Good. Now, let's move on. So now we are in single point cutting tool. So let's discuss in detail about the geometry of single point cutting tool. So this is what is single point. Why it is single point? Because the cutting edges, right? We have seen the cutting edges, right? We have seen the cutting edges here, the cutting edge here, and this cutting edge here, and these two cutting edges, and especially this is the cutting edge that will be in contact with the workpiece, and this cutting edge is this cutting edge here, tool. So if you are seeing the tool in this direction, we can see it in this one, right? Okay, so now let's understand the geometry. Why we have to do like this? Before understanding the geometry, let's see what we have. Some three important faces, or we can say flanks on the single point cutting tool. What are those? Okay, so let me highlight this surface here, right? This surface here, see this surface, and we have, let me take another color here. Okay, let me take green, this surface, and red, this surface, right? Or we can say them as flanks. Okay, so let's write them. So this is your rake face. Don't worry what is rake face and not, don't worry, we'll discuss them again, but just see what is the nomenclature here. And then this is side face, and this is the end face, or end flank also. Instead of face we can write as flank also, no problem. So generally end and side are known as flanks. Let me write them as flanks. Blank. Blank. Okay. And the holding one is called shank. This is called shank, where this holder is used to place this tool into the tool grip. You know that cutting tool you have to put into the some kind of tool grip, right? So here you use this shank and you place the shank there. And here these three faces have to be made from some kind of material. So three faces have been made. Why three faces? Why these three faces are important? We'll discuss them. Right? Okay, this shank I told you it is put into the tool post. You know, the tool post is there. You put that into a tool post for holding tool. So if the same thing, if I look at here, so this is the rotations RPM of the workpiece. Unmachined and machine one is there. Clearly, you can see that. Right? And I will just make some kind of notations here to make you understand what is what. Right? So let me write this edge. Okay, the color is not matching. Let's take some color. This one, this edge, this one, right? One. So let me write this as 1. This is 2, and this is 3. Same thing. I'll put it here, right? Let me take some other color, right? So if you try to make what is 1 here, so this is 1, this is 2, and this is 3. 1, 2, and 3. Okay. So the edge between 1 and 2 is known as side cutting edge. The edge between 2 and 3 is known as end cutting edge. Okay. So let me write them. 1, 2 is side cutting edge. Sometimes main cutting edge. Sometimes principal cutting edge. Cutting edge. Main principal cutting edge. And 2 to 3 is known as end cutting edge, or sometimes known as secondary cutting edge, sometimes known as auxiliary cutting edge. Good. Now, so once we know that there are 3 different, faces, okay, flank or faces, why these are made, what is the importance of that, we're going to discuss now. So what is the importance? If you see, for effective and efficient machining, these 3 are very important. What are those? First one, only the cutting edge should be exposed to the workpiece. You have this complete cutting tool. I want only the cutting edges. So this is one cutting edge here. If you see here, this is one cutting edge and another cutting edge, right? So these cutting edges only must be or these are the ones which should be in contact with the workpiece. Okay? You have this complete thing. It should not have any surface or nothing has to be in contact. Only these 2 cutting edges. So if you see the same figure here, 1, 2 or 2 to 3. Only these 2 cutting edges, I mean side cutting edge or end cutting edges, must be in contact with workpiece, and rest of the complete workpiece should not be in contact with the workpiece. That is the aim number 1 for efficient and effective metal cutting in the case of single point cutting tool. Okay. So if you see here, let me draw them also. Let me take a small line. Okay. If you see here, So this is important. This is important. Let me take some blue line. Take a line. It's not visible. Let's try it with some other color. Red. Okay. Right. So this is one of the cutting edge, that is main cutting edge, and this is another cutting edge, that is side or auxiliary cutting edge. Only these two cutting edges have to be in contact with the workpiece. That is aim number one. Okay. So if you see for these, you will be having some kind of depth also here. So you'll be having some kind of depth here, some kind of depth here, right? Right. Sorry. Okay. But my importance is only the cutting edge. This one, this and this have to be in contact with the workpiece. Okay. Only, I'll highlight again. Only this and this has to be contact. The shaded one should not be in contact with the workpiece. For that, what we have to do, we'll see. It means that these shaded ones have to be given inside. You have to push inside. It's generally, if it is perpendicular to this, then it's okay. But you have to push this inside. Then you're creating some two angles for that, right? You're creating this surface, and this surface. You have to push inside, some tilted inside, so that only cutting edges will be in contact with the workpiece. Good, right? So it means that I can say that you can just give some angle here, give some. Okay, let me take some other this thing. It means that you can give some angle here, give some angle here for that surface faces. Two angles. Remember, here we are giving two angles so that only cutting edges are exposed to the workpiece. Next, flank faces must be relieved from the workpiece. What are the flank? End flank. See, we have seen flanks, right? End flank and side flank. These flanks have to be different. It should not have any contact with the workpiece. For that, what I'll do, I will tilt them inside. If you see, there is some angle here. So let me take which color? Okay, this color is fine. So this is some angle. Can you see this is some angle? And for here, this is some angle, right? So this is an angle and this is an angle. Angle and an angle. So this is for this. This is for this. And the last one is chips must flow away from the machine. So if the top one, this face, if this one, okay, I'll take some other ink. If this face is not bent, the chip will come like this. I don't want chip. I want chip to go up like this, right? For that, on top face also have to give some inclinations, and that inclinations will help my chip to flow away from the machine, away from the machining zone. In the sense, it won't go back into the machining zone, or it won't drop it, or it won't curl and come inside. So that is what is important. For that, again, I'm going to make some two more angles. right? So here I'm making 2 angles, here I'm making 2 angles, here I'm making 2 angles. Total, I have to make 6 angles so that my effective and efficient machining process will be taken care of. Okay. So let's write this again. So of course, this is tool. This is work rotation, right? And maybe I'll say this is the axis at which the rotation is happening. Okay, and I can say this is the chip. Okay, chip I'll take different color so that it will be easily identifiable. Away from the machining zone. It should not come inside. Okay, 2 more angles. So this belongs to this. Right? 2 angles, 2 angles, 2 angles. So that your effective and efficient machining will happen. That's it. Simple fundamental thing. Okay. Now, how do you make these angles? I have, let us say, I have some kind of, okay, let me draw it clearly. So I have some kind of, like this. From this, I want to make this cutting tool like this. So this face, that face, and another face are there. 3 faces are there. So you have to make some angles. 2 angles I have to make. In each face, I have to make 2 angles. How do I make that? I'm going to remove the material, right? Let us say I want to make this angle like this. I want to go inside like this. If I want to go inside, I have to remove the material. How do I remove the material? I have to remove the material by using some process, machining process. I'll be using grinding here. Okay, I'll be using grinding. So let's discuss that. To ensure effective and efficient constraints that you have put here, right? All the surfaces are sloped or given the angle by using grinding process. So finally, the diagram looks like something like this. Okay, let me draw the diagram. I think you'll be understanding what I'm trying to do. So let me draw the diagram first. Okay, so it'll look something like this. Okay, like this. Like this. This. Okay, this is the diagram. Okay, so if you see here, you made 2 angles in this, right? And you made 2 angles in this plane or this face. And you made 2 angles in this plane. Okay, all these angles are visible, and this will make your cutting edges so that efficient. So this will clear your workpiece from rubbing, and this angle on that will make sure that your chip is flowing away from the machining zone. All these things are happening here. Okay, So I can say this is your shank here, and this is again I'm representing, this is your side flank, sorry, side flank, this is your end flank, and this is your rake face. Good. Okay. So when you have all these things, so side flank 2 angles, end flank 2 angles, rake face 2 angles, each one is having different specific purposes, right? So all these 6 angles, and there is one more thing that is called nose radius. So if you see here at this tip here, let me use this. At this tip here, it's not a sharpened one, it's having some radius, and that will give you nose radius. It's a radius that you're giving so that there is some usefulness of nose radius. It should not be too curvy, or it should not have sharp edge. It should be a little radius, has to be some kind of fillet has to be provided at this edge so that the machining is done properly. That we'll discuss. Why you have to provide nose radius, we'll discuss. Okay. So with the 6 angles along with nose radius, if you write them in a sequence, I mean, see angle 1, angle 2, angle 3, like that, angle 6 and nose radius in a predefined sequence, we call it as tool signature. So let me write that point. Okay. When all 6 angles along with 1 nose radius right, are written in a predefined sequence, then it is called as tool signature. But which angles, which angle is making what with what, all these things are important. But if writing them in a predefined sequence, then it is known as tool signature. Good. Now let's go and discuss something about excuse me, tool signature system. As we discussed about tool signature, we are going to discuss about tool signature system. We are going to discuss 2 tool signatures. In single point tool itself, cutting tool itself, we are going to discuss 2 tool signatures. One is ASA tool signature system, another is ORS tool signature system. So ASA stands for American Standard Association System. ORS system is orthogonal rake system. So we are going to discuss these tool signatures separately and then try to connect them and convert from one signature to another signature, and why, which signature is useful for what, or what are the advantages of ASA and what are the advantages of ORS, when we are going to use ORS, when we are going to use ASA, are we going to use ASA, are we going to use ORS, what is important, why, and all these things we'll be discussing in the coming slides. Okay, now next, right? So let's discuss the ASA tool signature system. ASA. If you see here, this tool only, from the top view, right? From the top view, this is what is the tool. The below one is the tool. And we are making three mutually perpendicular planes. If you see, these are the three mutually perpendicular planes. These are the three mutually perpendicular planes. And this was your shank, and this was your main cutting edge. This is your auxiliary or secondary cutting edge, right? End cutting edge, right? And if we have a plane which is parallel to this plane, so if you say, if we have a plane, if we have a plane parallel to this one, that is what is this plane, right? And that is what is your reference plane. That is what is your reference plane. And a plane which is perpendicular to this reference plane, there can be two perpendicular planes, and one plane is this, another plane is this. So one plane, this can be written as pi. So reference plane can be written as pi r. This plane can be written as pi x. This plane can be written as pi y. These are the three mutual perpendicular planes. And these three mutual perpendicular planes are with respect to machine reference. These are machine reference with respect to machine, right? So let me erase and write them again. Right? So let me write them. Right? So this is pi x plane. Oh, first you'll write here. This is pi r plane. This is pi x, and this is pi y plane. Okay. So if you can see here, I will write the axis also. Then you'll understand what is what here. So let me take some point here. Here. So if you are going along this, you're going along this. This is what is your y-axis. If you're going along this, this is what is your x-axis. If you're going along this, this is your z-axis. This is x, y. So x, m reference, y, m reference, z, m reference, machine reference. Okay. So with respect to machine references, you form some three mutually perpendicular. XY plane is pi r, YZ plane is pi y, ZX plane is pi x plane, if you remember. Okay. So let me write them. What is what here? Okay. So let me take some pen here. So pi x plane is machine longitudinal plane. Okay, before that, let me write machine ASA. What is ASA? ASA is American Standard Association. Right? So this is based on machine reference system. Machine reference system. Those are XM, YM, and ZM. So these are all fixed with respect to machine. From there, we are going to work out. So what is pi x? Pi x is machine longitudinal plane. Very important. If you are understanding this, everything is clear. Pi y is machine transverse plane. Or I can say traverse. Pi z is machine reference plane. Good. Okay. So how do you identify pi x, pi y, pi r? So basically you have this pi r. From there I can just start building this pi x and pi y planes. That's it. Okay. Good. So please try to understand. A as a tool system will follow basically three mutually perpendicular planes. In that planes, we are going to find now angles. Now we are going to find some angles that's different. But first, we are going to make some planes. First, we have pi r plane. From that, we are having two mutually perpendicular planes which are along the machine axis. Those are pi x and pi y planes. Pi x is machine longitudinal plane, pi y is machine transverse plane, pi z is machine reference plane. Good. Now three planes are there, tool is there. We will cut the tool with respect to each plane and see the projection of that plane, and then we'll find out the angles. Okay, good. Let's do that. Okay. So if you see, that is a tool, just we have rotated it. So what is this plane? What is this plane cut? You have cut this plane, the top one, right? The top one, the pi r plane. You have cut the plane with pi r plane. The tool has the pi r plane. We have just parallelly removed downside, and that is what has cut here. So this is what is your pi r plane. Pi r plane. This is pi r plane. Please remember. Once you cut the pi r plane, the top portion is removed. This is what is left out. So if you want to draw that, let me draw that. Let me draw that. It will look something like this. Yeah, something like this. Then there is a nose radius, right? And then something like this. This something like this, and something like this. Okay. So what are the angles we can see here? There are some angles that we can identify here. So what are the angles here? The angles are these ones. With this, we have some angle like this. With this, sorry. With this axis, we have some angle like this, right? And these are the angles. And what are the angles? This is what is this edge. This is what is your main cutting edge, end cutting edge, and this is your side cutting edge. As this is side cutting edge, sorry, this is your end cutting edge, this is your main cutting, right? So we have seen that already. Just don't get confusion. So the first one is side, and then this is end, right? So as this is side, this is end, I will make these angles as this angle as Side cutting edge angle is represented by CE. End cutting edge angle is represented by CS. And we are on pi r plane here. This is your pi r plane, right? And we are cutting. So let us assume that this line is belonging to the pi r plane. Let us assume that this line is belonging to the pi r plane. So we are in pi r plane here, and this also is pi r plane. Yeah, pi r plane. And let us say we are cutting with pi x plane here, and so this is pi x plane here, and this is pi y plane here. So you might get confusion. Don't get confused with these things, right? So, oh, sorry. I just made confusion. This should be here, pi x, pi x. I'll write two sides. It will be easily understandable. So this is pi x plane, and this is pi y plane. So it means that this is plane, this is on pi r, this is plane, and this is on pi r. Okay. So we have two angles, and we can even identify the nose radius as well. So this is your nose radius r. So what are the angles that we identified by cutting the cutting tool with respect to the pi r reference plane? We got two angles: side cutting edge angle, end cutting edge angle, and nose radius as well. Right? So please remember, this is cutting plane, this is cutting plane, this is cutting, and this is cutting plane, pi y, right? So let us write what are the things that we have got from this angles. So we got CS, side cutting edge angle. It's called side cutting edge angle. C we got as end cutting edge angle. And R is nose radius. R is nose radius. Good. So basically, we are looking from the top view like this. This is the view. This is the view. Okay, good. Now, let's proceed. So we have cut with pi r. Now we'll cut with this plane. What is this plane here? That plane is pi y. So let's cut with pi y. So this is pi y plane here, right? Pi y, pi y plane. And if you're cutting with pi y, this red color one is there, right? And what are the angles that are identified here? Let's write them, right? So if you see here, okay, let me take some, okay, this green only. Let me identify if it is, see, should good or not. Let's see that. Okay. Okay, let me draw this first. Okay, this color is not good. Let's take another color. Let's take blue. Okay. 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 So this angle and sorry, wait 1 minute. Yes. Okay. What happened here? Let me tell you. This plane, this is the, can you tell which is the, what is this plane? This plane, yes. Whatever you are thinking is right. That is pi by, and this is pi r, right? So with this plane, this went this side. Okay, let me take eraser. Small eraser. So it went this angle, and here also it went this angle, right? And this angle is your relief angle, which is written as end relief angle. This angle is known as alpha b, that is your back rake angle. Okay, to identify it clearly here, again I'm going to draw here. If you see here, this was the original line on the tool, and this was the reference line. This was on the tool, and this was the reference line. Okay, so whatever you are seeing here is alpha b. Whatever you are seeing here is theta e. Okay, so let me draw the side view. You'll understand, like if you're looking from this view. So how you're viewing, let us see. The view is this side. This view. Right? If you're viewing like this, the diagram looks something like this. Let me draw that for you. So it looks something like this. Right? Something like this. And then it goes straight. It will tilt something like this. Go straight like this. Right? Right? And these are the angles. Let me make them angles. Okay. So let me make the reference plane first. Right? These are the planes. Okay. So this is the angle here. Inside, you're going inside. Alpha b. Inside, you're going inside. This is theta e. Hope now this is clear. Whatever I'm just making it. You're looking in this view, this view, this view. Right? So this is your side flank here. Right? And this is your end flank here. The end flank is not visible here. Okay, the end flank is this line. You can see from that line. What are the angles that we can see here? These are two angles. One is alpha b, that is back rake angle. Okay, let me write back rake angle. And another is end relief angle. two angles we got in the previous one from by cutting pi r plane. By cutting with pi y plane, we got two more angles, that is back rectangle and end relief angle. And next we are going to cut with pi x plane. So this is what is pi x plane, right? So this is pi x plane here. This is pi x plane here. Let me write it here. Pi x plane. Okay. Now, if you're cutting with that plane, you're getting this kind of red color surface. And now, what are the angles that are going to make here? These are the angles that are going to happen here. What are the angles? Let me draw them. Some ink here. So, already we have the inclined one, but the machine reference plane will be something like this, right? Already we have something like this here, but the reference plane, sorry, the reference plane something is like this here. It's a little inside, right? So something, the reference plane is something like this. So every time I'm drawing the reference plane, a little lengthier. Okay. So this is the angle, and this angle, sorry, this angle is side rank angle alpha s, and this angle is side relief angle theta s. This angle I can just project here if you want. I'll just take it here, here, same thing. So this is big line, this is the shorter line, same angle. I can just write it as theta s. Okay, good. So if you are viewing from this side, this is your view. So how it look like, right? Let me draw that. It'll look something like this. Okay. And so okay, let me undo this. This is the angle. This is the angle. Okay, and this is your end flank, obviously. This is end flank. Okay, and the angle here is your alpha s. The angle here is theta s. Okay, and these are the angles. Okay, good. So let me write what are the angles here. Alpha s is side rectangle. Theta s is side relief angle. Why these are relief angles? All these things we'll discuss. Don't worry. Good. Now that we have all the angles and nose radius, 6 angles, right? 2 angles here, 2 angles CE, CS in pi r plane, right? And nose radius also is visible in pi r plane. In pi y plane, we have back rectangle and end relief angle, right? And in pi x plane, we got side relief angle and side rake angle. Okay, good. Now I told you we are going to write all these things in predefined sequence, and then we'll make up to the ASA tool signature, right? So before that, each angle has to be written with respect to some plane and measured in some plane, right? So let's see that. Let's see that. So all these three figures I've put in one single place. So this figure, and this figure I've put it into the single place here. So let me nomenclate. Let me label them here. Label them here using some rating here. So what is this end cutting edge angle? So this end cutting edge angle is given as CE, right? This side cutting edge angle is given as CS. Side rake angle alpha S, side relief angle theta S, end relief angle theta E, and back rake angle alpha B. And where is that nose radius? Nose radius is given as R, or small r also is fine for me. Good. Now these things, so let me write them. So alpha B, alpha S, theta E, theta S, CE, and CS. These are the angles. So if you go, these are measured with respect to which planes. All these things are very important. So please try to understand measured with respect to which plane. So alpha B and alpha S. So you see here this alpha B and alpha S. This is pi r plane. This also is pi r plane. So this is the plane which has went inside. This is the plane that has gone inside. But both are measured with respect to pi r. This is pi r. This is pi r. So hence I can say these are measured with respect to pi r plane and pi r plane, right? And measured in which plane we are getting these angles. Alpha B easily we can write in which plane. Alpha B is in pi y plane, because in pi y plane only we are doing it. And alpha S we are getting in pi x plane, right? So we can write this one is we are getting the angle in pi y plane because we are cutting with pi plane, and this we are getting with pi x plane because we are cutting with pi x plane and getting the alpha S. So theta E, theta S. So theta E measured in which plane? Theta E is measured in pi y plane. So let me write that measured in pi y plane. And with respect to which plane we are measuring, right? With respect to which plane we are measuring. So theta E, where is it theta E? So you see, this is what is your x, xx, xx. Inside is y, xx, xx, right? So this is x plane. Theta S, theta S, again, you see, this is what is your pi y. We are cutting with pi y plane. Theta E is x plane cutting. This is y plane cutting like this. Okay. So theta S is pi y plane cutting, and it is coming in which plane? It is coming in which plane? It is coming in x plane. This is x plane. Okay. In the same way, CE, CS are visible in pi r plane. Can you see that? Yes, both are visible in pi r plane. So measured in pi r plane, but this is pi x and this is pi y. So both are cut, both are visible because we are cut in pi r plane and visible in pi r plane only. In top view only, these are visible. So let me write these are pi r, visible in, or measured in. But you see here, CE is with respect to pi x plane, CS with respect to pi y plane, right? So CE with respect to pi x plane, CS with respect to pi y plane. So this is what is important. Okay. So alpha represents rake angle, theta represents clearance angle, C represents cutting edge angles. Now, as I told you, all these things have to be written in a predefined sequence. And if you write that predefined sequence, and then you can get into the ASA tool signature. So what is the predefined sequence that we have to remember? The predefined sequence is this. Let me take a little bigger one. Black. Right. So alpha B predefined sequence. Alpha B first, then alpha S, then theta E, then theta S, then CE, then CS, then nose radius. Okay. So what is this? The first one is back rake angle. Back rake angle. And what is this? Side rake angle. Back rake angle. What is this? End relief angle. And what is this? Side relief angle. This is end cutting edge angle. Okay, and this is side cutting edge angle. And this is nose radius. Okay. So example, any example? So how this is represented? So in exam, how it will be given? So in exam, how it will be given? So it will be given like this. For example, they say that the tool signature in ASM tool signature, the angles are this. It will say some 5 degrees, some 7 degrees, some 10 degrees, some 12 degrees, right? Some 22 degrees, some 15 degrees, and some 2 del, right? And this 2 can be in mm or inch. So just here I'm mentioning as mm. So it means that 5 degrees is, right? This is your back rake angle, side rake angle, end relief angle, side relief angle, end cutting edge angle, side cutting edge angle, and this is your nose radius. So in examination, if this signature is given, automatically you should be able to identify which angle is what. Okay, so you might say that, like, so when I'm unable to remember this, so how do I remember this? There is a technique. There is a small technique. This is my technique, or people often use, not my technique. So many people use this, but if at all you like it, use it, or else if you have any other memory tip that you have to remember this thing, it's also fine. So this is how people follow it, how to remember. So how to remember it? So I just make some small this thing for you. So there are 3 couples, right? Couple 1, 2. Then couple 2. Then couple 3. And a bachelor. Okay. First couple is called as rake couple or rake angle couple. Second couple is relief angle couple. Third couple is cutting edge angle couple. The last one is nose radius, that is bachelor. Okay. In every couple, the second person is having SSS. Okay. I mean, I can say, I will write like this. S, S, S. Okay. In rake angle, we have side rake angle, right? So I'll write it as alpha S. Right? Rake angle is given by alphas. Please remember that these are alphas. Alpha, theta, C, and R. Alpha S, theta S, CS. And for rake angle, we have back rake angle, right? So let me write as back rake angle. For relief angle, we have, other than side, we have end relief angle. For cutting edge also, other than side cutting edge angle, we have end cutting edge angle. And then we have nose radius R. And that is how you remember this things, couples. Okay. So this is rake, relief, and cutting edge nose radius. So this is how you have to remember. You have any other memory tip? Generally, people use this. If you have any other memory tip, that's also is fine. You can remember it. Okay, good. Now, but there is some problem with this thing. There is some problem with this thing. What is the problem? The problem is nothing but we are measuring the angles. We are measuring the angles with respect to the we are measuring the angles with respect to the machine plane. I don't want that. Why I don't want that, I'll tell you. With respect to machine planes only, we are measuring this, we are cutting the tool and we are measuring the angles, two angles we are getting in each plane, and then we are getting nose radius in one plane extra, and that is why it's called nose radius R. That is a bachelor. Good. But what is the problem? So let's discuss the problem first. The problem is this. What is the problem? The problem will give you some solution, and that is what is ORS tool system. So that's why I'm discussing that here. So in force system, like if you're putting some, obviously when you have some contact between workpiece and tool, there is some force that is generated, obviously, right? So if the rotation is happening like this, okay. Now what is happening? There are, I mean, of course, there is this speed. I mean, if you're going in this direction, okay. If you're going in this direction, this is speed, right? So there are some cutting forces that are occurring at cutting edge. So this is your cutting edge. Let me take that. So this is where the contact is happening. Okay, where is that? This is where the contact is happening. This is where the contact is happening. Good. So what is happening? There are some cutting forces that are occurring. The cutting forces are along this edge. Okay. So what is happening? The cutting forces are along this edge, like this. Like this. Okay. So these are some cutting forces that are happening. So we didn't cut like this, right? In the previous case, we did not cut our this thing like this. This is your feed, right? This is your feed. Initially, we have cut it as reference plane, then perpendicular to that, it is cut like this. So now what is happening? There are some cutting forces that are happening here. right? So this is cutting force actually, which are like this are cutting forces. This will discuss why these are cutting forces. All these things we'll discuss when we're discussing about the force analysis. And these are your thrust forces. These are your thrust forces. Right? Okay. So these are your cutting forces and these are your thrust forces. If you remember, those are occurring with respect to this main cutting edge, right? This cutting edge. It's also known as side cutting edge. But you're not measuring the angles with respect to this edge. That edge is very important. If you see that edge, we are not making angles with that edge, right? See that angle. We are not making angles with that edge. That cutting edge is very important. This is the edge that is very important. So this is the edge that is very important. But how are we cutting? We are cutting it something like this. There is an angle, right? Can you see that? This is the main cutting edge. But you are cutting it like this. I don't want that. My Y plane is little inclined to this cutting edge. This is what is your cutting edge. So in AS system, we are using this system where the reference is happening with respect to machine. But in ORS system, we will use this cutting edge as a reference. So the plane, we are going to drop plane like this. Instead of this plane, we are making a plane with respect to this cutting edge. See, there is an angle between this pi plane, and this plane is known as orthogonal plane. Okay, so that is where the difference between ASA and ORS system will come into the picture. Okay, okay, right? See, so here please remember that this is FC is cutting force. FT is thrust force. So why it is called cutting force, why it is called thrust force, we'll discuss that in the lectures, right? So see, this is where the main difference will come. See, the plane is cut with respect to the cutting edge. So this is the cutting edge. And the plane is cut along that cutting plane. Right? Along the red down we are going. Let me highlight that red so that it will be clear for us. Sorry. See, that plane is along that red plane. That is what is your side cutting edge. And that plane is not orthogonal. Sorry, it is called cutting plane. Sorry, I just used wrong notation. I'm sorry for the before statement. I'll take back. This is what is your cutting plane IC. And perpendicular to that plane is called pi O plane. That is orthogonal plane. Cutting plane, orthogonal plane. And this plane is pi R plane as it is. We are not going to change that reference plane pi R, pi R, pi R, pi R. Okay. So instead of pi X and pi Y, we are making as pi C and pi naught. So that is the only and major difference. Okay. So that happily we have some cutting forces like this. We have some cutting forces like this. This is your thrust force and this is your cutting force. Okay. Right, like this. Good. So let's read the statement. During machining, forces either appear along the cutting edge or perpendicular to the cutting edge. But in A, obviously it is along the cutting edge only, right? This is along the cutting edge. So let me write the cutting edge clearly here. The cutting edge is this, red one, right? So in A's system, there is no plane along the cutting edge or perpendicular to the cutting edge. That's the reason why for force analysis, there must be a system in which plane should be along the cutting edge and the normal to the cutting edge. So that will make our study easy. Measurement of angles is difficult. That's okay, but our study will be easy. It will be making our life easier. But analyzing the angles will be a little difficult. Okay, analyzing the angles will be little difficult, but the study will be very easy. Because analyzing angles in the previous section, happily we have cut reference plane by r by x, happily we have done. But here the visualization of angles are difficult, but the analyzing part, the force analyzing part and rest of the parts are very easy. Okay, so that is where I'm going to stop for today. And so that is where this analyzing angles will be coming into the picture. So here also we'll be having some different tool system, a tool signature system, where the angles, two angles, one angle and nose radius will not change, but the other angles will be changing. And based on that angles, we will be analyzing the force, cutting force analysis. From there we are going to calculate the different forces and all these things. But ASS system is the system that is using please remember, ASS system is the system where we are using the machine reference system, and ORS system is the system where we are using cutting edge as our basic plane, and then perpendicular to that plane there is another plane that is called as orthogonal plane, pi O plane. So here I can write as pi C cutting plane and pi O orthogonal plane. Okay, so that's it, guys. This is a demo, but in a this demo, hopefully I made you understand the basic differences between single point cutting tool, multi-point cutting tool, and what are the examples of that. What is the syllabus of gate, especially in manufacturing. And then we have given a little start for ORS system. If at all we are going for the full-fledged classes, I'll be explaining these things in detail with more figures and schematic diagrams. Thank you for viewing this lecture. Have a good day. Is anyone here? Any doubts? Hello? Anyone who is viewing this lecture live? Fine. If no one is viewing the lecture, then you can view the lecture as a recording. Have a nice day. Thank you.